Welcome to the Explainer. Okay, today we are tackling something that is honestly one of the most fascinating and kind of frustrating mysteries in the AI world right now. We're constantly hearing about how incredibly smart large language models are becoming, right? But there is a massive elephant in the room here, and that is AI interpretability. Sometimes these highly advanced models just completely lie about their own logic. They'll give you a seemingly sound step-by-step reasoning process, but then their final answer comes entirely out of left field, totally disconnected from the work they literally just showed you. It's a huge trust problem. Because think about it, if we can't trust how an AI arrives at its conclusions, how can we rely on it for anything critical? Well, today we are going to look at a genuinely groundbreaking framework designed to fix this exact issue.
All right, let's dive into this. Here is our roadmap for today. We are going to start with standard chain of thoughts trust problem. Then, what exactly is faithful CoT? After that, we'll break down the two-step solution. And finally, we'll look at the actual results and limitations. So, part one, standard CoT's trust problem. Now, asking an AI to just think step by step has been a massive breakthrough in the industry. It definitely improves response quality overall, but it has a major, kind of hidden flaw. Let's read this math word problem together to see exactly where it breaks down. John plans to sell all his toys and use the money to buy video games. He has 13 Lego sets and he sells them for $15 each. He ends up buying 8 video games for $20 each and has $5 left. How many Lego sets does he still have? Now, this is the exact kind of seemingly straightforward prompt that actually really trips up standard AI reasoning. And honestly, the way the AI handles it is completely baffling. Just look at how the AI processes this. It actually does the math. It calculates that 13 times 15 is 195. It figures out that 8 times 20 is 160. It even tries to add the $5 left over. The AI is clearly showing you a chain of reasoning. But then, check out its final output. The answer is 0. Wait, what? It just confidently spits out a big red X of an answer that has absolutely nothing to do with the math it just spent time processing. So we have to ask the obvious question. Why does the AI's logic completely contradict its final answer? This right here is the ultimate unfaithful AI problem. It creates this crazy cognitive dissonance for us as users. The model shows its work, but it doesn't actually use that work to reach its conclusion. It's basically hallucinating the connection between its thoughts and its actions. If we can't verify that the model's decision-making actually matches the reasoning it shows us, the whole system just becomes an untrustworthy black box, and we absolutely need to resolve this. Which brings us to part two. What exactly is faithful CoT? You can think of this framework as the ultimate AI lie detector. This is faithful chain of thought, or faithful CoT. By definition, it's a reasoning framework designed to generate trustworthy reasoning chains by ensuring that final answers are directly derived from the reasoning process. Now, the absolute key phrase here is directly derived. We are fundamentally forcing the AI to prove its work in a way that mathematically guarantees the final output is a product of its reasoning steps, not just some random guess slapped onto the end of a paragraph. When you compare the two approaches side by side, the difference is literally night and day. With the standard chain of thought method, the process is opaque and unfaithful. You end up with a totally disconnected output, because it's really just generating text that kind of looks like reasoning. But with faithful CoT, it is transparent and executable. Because the output is directly derived from an actually executed process, it totally eliminates that terrifying disconnect between the AI's logic and its final answer. Okay, part three, the two-step solution. Let's look under the hood. So, how do we actually force an AI to behave this way? The crucial point is that faithful CoT breaks the whole thing down into two macro steps. Step one is translation. This is where the AI converts your regular natural language question into a mix of natural language sub-questions and strict symbolic language, like Python code. Then, step two is problem solving. This is where that symbolic language is handed off entirely to a deterministic solver to actually execute the math. Let's ground this theory in reality by bringing up a new math problem. We'll run this one right through our two-step engine. Daniel has 17 apples. Rosie gives Daniel 5 oranges, and in return, Daniel gives her 3 apples. How many apples does Daniel have now? This is a classic logic trap, right? Because of those completely irrelevant oranges. Let's see exactly how step one handles this. This is step one, translation in action. The AI takes the problem and creates a highly structured format. First, it writes out natural language sub-questions, like how many apples does Daniel have in the beginning? Then it notes the dependency. This first question is totally independent. And then the magic happens. It writes symbolic Python code for it. N begin equals 17. Notice it ignores the oranges completely. It creates another independent variable for the apples given, setting it to 3. And finally, for the answer, it creates a dependent variable, writing the Python code n begin minus n given. As our source material perfectly highlights, the natural language component breaks down the complex problem into simpler, independent subproblems. This approach is brilliant because it forces the AI to create a highly verifiable dependency graph. The AI isn't just writing a messy paragraph of thoughts anymore. It is architecting a logical blueprint where every single piece relies on a specific stated fact from the prompt. And that brings us to step 2, problem solving. Now that the AI has translated the problem into Python code, we take that symbolic language and execute it using a deterministic solver, which in this case is a literal Python interpreter. Because we are running actual code here, the reasoning chain is genuinely executed. The interpreter does the math 17 minus 3 and produces the highly verifiable, perfectly faithful result of 14 apples. The AI literally cannot hallucinate a wrong final answer here because the Python interpreter strictly follows the generated logic. Moving on to part 4, results and limitations. Because the real question is, does this hold up in testing? Well, this all sounds fantastic in theory, but the real-world performance results are also incredibly strong. When using a standard evaluation method called greedy decoding, Faithful CoT beats out all other prompting techniques in 8 out of 10 major datasets. It just absolutely dominates the competition when it comes to getting the right answer faithfully. Let's rapid-fire some of these key performance wins. First up, there is massive agreement with human annotators. When humans review the AI's reasoning chains here, they agree that the logic is sound and super easy to follow. Second, it is highly robust to the choice of exemplars. You know, in AI prompting, the examples you feed a model usually drastically swing its performance. But with Faithful CoT, even when random examples are used, the accuracy only fluctuates by a tiny margin, between minus 1.5 and plus 1.2. It's incredibly stable. But during the ablation studies, which is where researchers strip away parts of the prompt to see what breaks, they asked a really surprising question. Do the natural language comments we saw back in step 1 actually help the AI solve the problem? When researchers compared a full prompt that included all those helpful natural language sub-questions against a prompt that forced the AI to only output the symbolic Python code with no natural language at all, the outcome was fascinating. Surprisingly, removing the natural language completely doesn't significantly drop the AI's accuracy, except in one specific dataset called clutter. It turns out those natural language comments make the reasoning highly interpretable for us, the human end users, but the AI itself doesn't actually heavily rely on them to get the math right. And this brings us to the core limitations of the framework. Yes, the math-solving part, step 2, is perfectly faithful and deterministic. But step 1, the translation stage, is still opaque. We honestly still don't fully understand how the large language model generates that Python code and reasoning chain from the initial question. It is still a black box, translating a prompt into code. And as we just learned, the natural language comments that make us feel so good about the AI's logic don't actually heavily boost the model's performance. Ultimately, Faithful Chain of Thought is a massive leap forward. By separating the reasoning translation from the deterministic problem-solving execution, we have successfully forced the AI to prove its math, preventing those wild, unfaithful hallucinations at the finish line. But it does leave us with this really provocative question. If the initial translation stage inside the AI's brain is still a black box, can we ever fully 100% trust the machine? It is a fascinating challenge for the future of AI interpretability. Thank you so much for watching this explainer, and keep questioning the logic.